Now we want to talk about parallelization strategies. Given that arbitrary list operations can't occur in parallel, how do you make sure that the things that need to execute serially do and the things that need to execute in parallel can go in parallel? Well, the simplest way to do that is to make sure that any operation that is doing a write is not occurring at the same time as any operation that's doing a read. In other words, any operation that does a read can work in parallel with any other operation that does a read, but as long as one of the operations does a write, it needs to work by itself. That's called parallelization among readers. The second approach is to say, okay, certain parts of an operation need to make a change. So when we detect that we need to make a change, we'll lock the whole list, and then nothing else can go on in parallel until we finish what we're doing. That's called the global lock approach, and of course the difficulty with that is that it locks the whole list and means that multiple operations that are making changes to the list can't occur in parallel. We can get around that if we use a finer grained locking approach where we associate a lock with each node, and then an operation only locks the nodes that it needs to manipulate. The difficulty with that is that it's more complicated to control because we have to worry about deadlock, among other things. If one operation needs one node and is using one node and needs another node, and the other operation is using the other node and needs the first node, then we've got a potential for deadlock. Okay, so let's take a look at the strategies one by one. Parallelization among readers is fairly easy to implement. The basic idea is that read-only operations can occur in parallel, but any operation that makes a change, let's say that inserts something or deletes something from the list, needs to execute sequentially. We enforce that by creating read locks and write locks. A read-only operation acquires a read lock, and a write operation acquires a write lock. If we have a read lock in effect on the list and we request another read lock, then that lock can be granted. But if a read operation is in effect on the list and a write lock is requested, it can't be granted. The process that's waiting for the write lock needs to wait until the read lock is released. And if the write lock has been granted, then we can't grant either another read lock or a write lock until that first write lock is released. So a couple of examples below. If we're doing a search, that doesn't change the list, so we can acquire a read lock at the beginning of the operation and release the read lock when the operation is about to terminate. If we're inserting a node in the list, then that's going to modify the list, so we need to acquire a write lock and release it before we finish the operation. Now with the global lock approach, each operation has two steps, traversal and then list modification. So for the first step, it walks down where it needs to be in the list to do the operation, either inserting, deleting, or finding something. And then the second step is to perform the modification needed on the list in case of a deletion or an insertion. So the basic idea is that we want to perform the traversal in parallel. Even an insertion and a deletion can traverse the list in parallel, but when they get to where they need to be, they need to lock the list. So the list is modified between the time a write lock is acquired and that same write lock is released. Everything else needs to wait for that critical section to finish. If I say everything else, every other writing operation needs to wait for that critical section to be released. Now the problem with this, or the potential pitfall, is that if you're doing a check is to see whether or not anybody else is modifying the list, and then having determined that nobody else is modifying the list, you try to grab the lock. You're not assured that some other process doesn't grab the lock in the meantime. So after you think you've got the lock, you need to revalidate your assumptions. Let's see how that looks in the code. We're looking at the code for insertion again. We perform the traversal, we acquire a write lock, and then we check to make sure that no other operation has changed the nodes that we need to work with to do our insertion. We need to make sure that the node is still there and the link from pointing out of the node still goes to a valid node. Because if that next node on the list has been deleted, then we got to start over again. We got to retraverse the list, etc. We've got to repeat the traversal if we can't go and do the insertion at this time, and then at some point after trying and trying again, we'll get to the point where there aren't any conflicting operations going on, and then we can modify the list. And of course, after we're done modifying the list, we release the right lock. The fine-grained locking approach works this way. Instead of there being a lock on the whole list, there's a lock with each node, and you can either read lock a node or write lock a node. Each operation locks only the needed nodes. So operations now can execute in parallel, except when they conflict on some nodes, which means that at least one of the operations needs to have a write lock on the node. Nodes that will be modified are being write locked, and nodes that are read and must remain unchanged are read locked. So this avoids the concurrency problems, but it creates a possibility of deadlock. Again, if one operation is reading node A and then attempting to modify node B, while another operation is reading node B and attempting to modify node A, then both of them get the read locks and they try to get their respective write locks, and they can't do it because the other operation has that node read locked. So there's nothing to do but wait and wait and wait forever. So that's a deadlock, but we can avoid deadlocks by imposing a global lock acquisition order. Let's say if we say that you have to acquire all locks in order of increasing memory address. That will solve the problem because you can't have a chain of locks, each one of which has to be acquired before another lock. You can't have a circular chain like that. Now let's look at how a fine-grained locking approach works with insertion. We see this method here that's to insert a node in a list, and notice what it's doing. It's attempting to insert the node at the head of the list or between prev and p. In other words, we traverse the list to determine where to insert it. That could be at the beginning of the list, or it could be between two nodes, which we'll call prev and p. The previous value of the node p and then the node p. So the first thing we do is acquire a write lock on prev. Why do we need a write lock? Well, we need to change the next pointer from this node to point to the new node that we're going to insert. And then the next thing we need to do is acquire a read lock on P, because we can't have anything changing that node while we're trying to insert a pointer to it from the new node that we're trying to link in. Then we need to do the check to make sure our assumptions are still valid. The first thing we need to check is whether the next field of the previous node of node prev, P-R-E-V, points to node P, and if it does, that's okay. We also need to check whether previous has been deleted, and if it has been, that's not okay, or whether P has been deleted, and if it has been, that's not okay either. If any of these checks don't pass, then we do what's in the body of the if right here. We release the two locks that we have acquired, and we repeat the traversal, and then we try again. But if these checks all pass, that is to say that the previous node does in fact point to the current node, and neither the previous node nor the current node have been deleted, then we set the succeed variable equal to 1, and we drop down and actually perform the insertion. So in order to perform the insertion, we need to check whether prev is null, and if so, then the new node becomes the first node on the list. Otherwise, we just link in the new node we've created between the previous node and node P. After we're done there, then we release our write lock on the previous on node prev and release our read lock on P. A couple of questions about the code. I said we have to make sure that neither the prev node nor P have been deleted. What do these checks actually check? Each node has a deleted field, the field that's called deleted, and so the check simply checks the deleted field to make sure that it doesn't say true, and if so, it concludes that the node has not been deleted. Now, you might ask, why do we have a deleted field? Why don't we just delete the node and not worry about it, just get rid of it? Well, the answer to that is a little bit more subtle. Nodes can only be deleted when they're not involved in any operation. We know that this node is involved in our operation, but we can't conclude that it's not involved in any other operation. In other words, if let's say somebody, or actually maybe 2 or 3 other transactions are trying to insert another node in front of this node that we're trying to delete, we can't conclude that we're the only thread that has the node locked. And if there are other threads that are trying to perform this operation, whether or not they've been able to acquire the lock, if it's a write lock, only one thread can acquire it at a time. But we can't get rid of nodes as long as some other operation is using them. And so if we wanted to actually delete them right now, we'd have to keep track of how many other threads were using them. Well, that would require reference counts on each node. When you refer to a node, you increment the reference count. And reference counts are generally pretty expensive, so it's much easier just to create a little deleted field in the node. We can check that. And then if the deleted field is set, we don't link any other node to that node. And then when garbage collection comes along, there will be no references to that node, so the node will be deleted then. So we can't get rid of nodes right away because we don't have a way to ascertain that there are no other operations involving them. Okay, now let's look at the delete operation. It's very similar to the insert operation. The only changes are what I show in black here. If the code is the same, I showed it in green. So instead of trying to find a node to insert, we're trying to find a node to delete. When the node has been found, we perform the deletion. And when we delete, we've got to acquire 2 write locks, not just one. We've got to delete node P, and so we need a write lock on it. And also, we've got to change the pointer from the prev node, so we need a write lock on it too. The only other differences are down here where we actually perform the deletion after ascertaining that all of the conditions still hold. We have to acquire a write lock on the header node if we are trying to delete the header node. Otherwise, we delete the non-head node, and we do that with the lock that we already have set on node prev. Then we just set the deleted field of that node to be 1 because, as we said, there might be another operation that's in progress on it. And so then we release the write locks and we're done. So that's the third way that we can control concurrency with fine-grained locking. So we've seen 3 ways. First of all, we've seen parallelization of readers. Second, we've seen global locking. And then we've seen fine-grained locking. And as you can tell, the code gets longer each time, but the performance gets better because more operations can occur in parallel.